Welcome students to this next session on industrial metallurgy. This is session number 33 and these are the contents that we'll cover in this particular session. Uh, you see, like the type 2 binary alloy systems, which were eutectics, type 3 systems are also eutectics, and on the basis of the eutectic reaction, these alloys are also categorized into three categories: the eutectic alloy, the hypoeutectic alloys, and the hypereutectic alloys. And particularly if we talk in terms of the lead tin alloy series, the eutectic alloy is of eutectic composition 61.9% tin, remaining lead. All alloys to the right of it are called hypereutectic alloys, and all alloys to the left of this composition, which have less than 61.9% of tin in them, are the hypoeutectic alloy. So we have already shown it on the diagram also. Again, for your reference, I'm repeating it. These alloys are, this is the eutectic alloy. Oh, I wrote it wrongly. This should is hypereutectic alloys. And here on the left, we have hypoeutectic alloys. So the purpose of this session is to discuss the equilibrium cooling of the hypoeutectic alloys and then of the hypereutectic alloys. The hypereutectic alloys would be taken in the sessions to come. But the main difference between the equilibrium cooling of hypoeutectic alloys done for type 2 alloy systems and now being discussed for type 3 systems is that in case of hypoeutectic alloys in type 3 systems, there would be further three categories of alloys within the hypoeutectic alloys only. So see, right from this composition till this composition, all alloys are hypoeutectic alloys. Now we have put them into one category, but just taking one case in this entire range will not be suffice to explain the equilibrium cooling of hypoeutectic alloys, because hypoeutectic alloys, here the hypoeutectic categorization has been done just on the basis that all these alloys have got less than 61.9% of tin in them. But among these various hypoeutectic alloys, there are some differences, and there are three separate classes that would be formed. For example, for alloys of lead and tin, hypoeutectic alloys which have tin in the range of 0 to 7%. If you talk about the room temperature microstructure, at the room temperature, they'll be lying in the single phase region and would have only one phase in them, that is alpha solid solution. But if you talk about alloys from 7% to 19.5%, if you come down and see what is going to be the room temperature microstructure, see they are lying in the two phase region alpha plus beta. So they will have two phases in them, alpha solid solution and beta solid solution. But importantly, these alloys would not have shown eutectic reaction, because when they reached the eutectic temperature of 183, they didn't have any liquid solution in them, and without liquid solution of eutectic composition, the eutectic reaction cannot occur. So these alloys, though they have the first category of hypoeutectic alloys had only one phase in them, alpha. The second category between 7 to 19.5% tin that I am talking right now contain two phases in them, but that is without eutectic reaction. And the third category of hypoeutectic alloys would be 19.5 to 61.9. And if you look at these alloys, like the last category will lie in the two phase region alpha plus beta, but some of that alpha and beta would have come through the eutectic reaction. So there are three categories of hypoeutectic alloys in type 3 alloy systems. So we particularly if we talk about lead tin systems, we have hypoeutectic alloys, the first category having tin in the range of 0 to 7%. And then we have the second category of hypoeutectic alloys containing tin in the range of 17 to 19.5%. And in the third category of hypoeutectic alloys, we have tin between 19.5 till the eutectic composition, that is 61.9% tin. So let's take the first case and let us discuss the equilibrium cooling of these first category of first category. Similarly, students, if we go to the hypereutectic alloys, in the hypereutectic alloys also, all these alloys from 61.9 to 100% tin are hypereutectic alloys. But we'll have further 3 subclasses. One category of hypereutectic alloys will have tin in them from 61.9 to 97.5. Then we have the second class of hypereutectic where tin would be in the range 97.5 to 99. And then we'll have the third class where we'll have tin in the range 99 to 100. These 3 categories have been mentioned by me over here, right? So let's now start discussing the equilibrium cooling of a hypoeutectic alloy. And I said there are 3 categories of hypoeutectic alloys: 0 to 7, then 17 to 19.5, and then from 19.5 to 61.1. 60. So I'm taking the first subcategory of hypoeutectic lead tin alloys with you, 0 to 7%. For example, just for illustration, we have taken an alloy which contains 95% lead and 5% tin in it. So I mark this composition, draw a straight line right till a high temperature. When the alloy is in the molten state, I am at point L. So if you try to find out the microstructure of this material at temperature corresponding to point L, the microstructure contains liquid solution. This is the composition, this is the relative weight. We start cooling this alloy under strict equilibrium conditions. No change occur in the microstructure till we have reached point M, which represents the liquidus temperature of this alloy. Solid phase begins to appear in this alloy with the formation of what is there in this region, alpha. So solid phase appears in the form of alpha solid solution. Drawing tie line, you can find out what is the chemical composition of the alpha phase. And you know that when the first solid phase appears, we generally write that its relative weight is 0.01%, remaining is still liquid. So 99.99% is still liquid, and liquid's chemical composition is slightly shifted from this 95% lead and 5% tin composition. Then when we come to a lower temperature, say corresponding to point N, the critical nuclei, the solid phase would have grown and would have taken the shape of dendrites. The amount of solid phase would have increased. Here it was 0.01, now it has become about 18%. The chemical composition of both the solid phase as well as of the liquid phase is changing, you can see. Then as we drop down the temperature and we reach point O, this represents to the solidus temperature. So just above point O, or just at point O, when we are still slightly above the solidus temperature, the last traces of liquid phase are present in the alloy. Again, drawing the tie line OZ, you can find out what is the chemical composition of the liquid phase, what is the chemical composition of the solid phase. Importantly, at this solidus temperature, the liquid is last traces, the solid is nearly solidification is complete with 99.99 weight%. When your temperature drops a fraction below point O, the solidification is complete. So at point slightly below O, or at point P, or even at room temperature Q, the solid phase is completely there, and you see that our material system is in a single phase region, and that single phase is alpha solid solution, and that alpha solid solution has to be exactly the same as is the alloy composition. We had taken a 5% tin alloy, so this alpha is also 5% tin, and it is 100% by weight. Now in the next session, we'll discuss the equilibrium cooling of a hypoeutectic lead tin alloy, which has in it tin in the range 7% to anywhere between 19.5%. And in the subsequent section, we'll discuss the equilibrium cooling of a hypoeutectic alloy, which has tin in the range 19.5 to 61.9. And in the session next to that, we'll discuss the equilibrium cooling of the hypereutectic alloys. I hope you have understood this. Thanks for watching this online session.